kick off the recording, and then Sean, why don't you just give yourself a little demo for us, and then jump into it, okay?
Sure. All right. If I can get the right buttons, I can share my screen. All right. So yeah, my name's Sean Whitesell. Been a Microsoft MVP for a few years. I'm now a senior cloud architect with a company out of St. Louis, Architect Now. And we're a cloud solution provider that provides custom app development for any kind of project needs, specifically towards Azure. Although it's funny, right after I hired on, I ended up doing some AWS projects, which was also in my wheelhouse. So that was awesome at the same time. Tonight, we're going to talk about network fundamentals for developers. And I had to be kind of careful on the title of this because I want to make sure it wasn't networking for developers, and because I didn't want it to come across like I'm trying to get introverts out of their house or to make them talk. And because I know that's also near impossible. Saying that as I'm a recovering introvert myself. So the goal for this is to better understand how networking occurs, how computers talk, and this kind of came about, the idea came about when I was sitting in on some interviews and somebody would ask the candidate, because they were doing some web development stuff, and they said, all right, if you type a domain name into a browser, how does it get to the server? Just tell me, and doesn't matter how much detail or anything, just tell us what you know about how the internet works. And so many developers have no clue or very limited ideas or understanding of how the internet actually works. So this is an attempt to kind of bridge that gap, so to speak. So we'll go in and kind of jump into this. And since everybody's familiar with some of the devices in your house, maybe you still have a server, and a lot of people don't anymore. I used to have at least 1 or 2 servers in the house, but got laptops, we've got our router. Hopefully you did not buy it at Walmart. Maybe you got hopefully a higher quality router. And of course, now we get more and more laptops and smart TVs, and then our game stations, right? And it's constantly growing with the number of devices in our house. And for whatever reason, even our dirty laundry has to get on the internet, and not even through social media. They're skipping that and going straight to the washing machine. So we have all these home devices that are trying to talk to the internet, and they go through this router. And we'll start here with understanding, first off, that a router has essentially 2 sides. You have the LAN side, the local area network side of it, and that's where your home devices are going to be at on the inside. And then you have what's called a wide area network, the WAN. And now, for the most part, we're just going to say that that's the internet. That's the most common thing that everybody's familiar with. So you just have this, in a sense, a gate between the home devices and the internet. And when home devices need to talk to each other, like I said, maybe you got a laptop talking to a server, or like a video media server type thing, well, it's going to stay on that inside, and it doesn't go to the internet. But a lot of times, certainly like we're doing right now using Zoom, where we've got some sort of device that is going outside the router and it's going to a website. And it is sending a lot of packets from these devices out to the internet to reach different websites, be it Google or Bing or Facebook, etc. We have these packets that are coming from or back and forth between through that router and in between devices. Now, I mentioned packets, and I want you to kind of think of packets as very similar to like a passenger train car, where you have a lot of data that needs to be broken up, but only so much can fit in certain kind of, let's say, a vehicle like a passenger train car. And these packets are sent across, and they've got information about the things that are inside, about the payload, for each car, and each car is, like a serial number and such. And as it's going through one device to another, it's inspected, and to make sure it's on the right route and things like that. And if we get into something like TCP, which I'll talk about a little bit later, you can see how it does a lot of extra work trying to make sure that that data is correct. But when we go to something like the browser and we type in google.com, that's not an address, that's simply an alias to an address. And that uses a system called the domain name service, and or domain name system, depending on where you're seeing that. So the domain name service is responsible for handling the lookup between a name and an IP address. And you can use something like ipconfig /display DNS on your Windows machine. You can see the DNS information that's there. Sometimes you'll find that you need to flush the DNS, have that start over completely, so that it's going to basically clear that address book, if you will, and start over. Now, the quickest example of this is we're all familiar with using our smartphone, and we have a hard time now anymore remembering a ton of phone numbers. Instead, we just look it up in our phones. So if I'm going to call up my buddy Michael Perry, I'm going to find his name in the contact list, and it will come up with that number, and then I can dial it or share it, whatever. And yeah, that's not a real number. In fact, Michael does charge a lot for his time, so be careful if you dial it and he answers. Now, with DNS, there are different types of records. The most basic one is the A record, the name to IP. So now that's that like google.com changed out to a specific IP address itself. And we're going to talk about what an IP address is in just a moment. And then a CNAME is also an alias, but you can think of it as, if I have google.com as the A record, www.google.com is the alias, or the www is the alias for that same IP address. And there's also MX records for mail exchange, as well as other ones out there. Again, on Windows machines, you can use a program that's most likely already installed, is NS lookup. And if you set type to NS, you can see the name server information, or if you change it to MX, you can see the mail exchange information, etc. The quad A is if you're using IPv6, IP version 6 in there, which I will talk briefly about IP version 6. It's really just a different sizing of the address pools. So I have a friend of mine, Sean Weisfeld, that runs usergroup.tv, and I put all of my user group videos on there on that website. He helps me share those. And if you were to do an NS lookup on usergroup.tv, you notice that there's 4 different IP addresses, and what's called there's 4 octets. So 185 is one octet, 199 is another octet, 108, then 153. And you notice that these 4 addresses only differ on the 3rd octet. Now, that is simply, however, that hosting provider has been set up. Not sure exactly why they did just on the 3rd octet, but not everybody has that. Usually you'll see one address, but if you were to do NS lookup on google.com, you'll actually find different IP addresses. It all depends too on where in the world you are as to which ones you may get for Google, because they have many different name servers out there to help resolve that, to help share that load. So if I'm going to send some information over to Michael, and I'm going to give you kind of a light analogy, and this is mainly for routing. Now that we're getting into how we're going to get packages of information out from one spot to another, and I know I've got some data that I need to send, and I did update this slide just a moment ago, and I did forget one piece. So when I have this package I need to get to Michael, I need to find out the address, and of course I forget one. I was supposed to change out Chad Green because I was picking on somebody, a friend of mine over in Louisville, Kentucky, and I forgot to change that name out. But and there's not supposed to be any snow there in Texas. So that's what I get for rushing through this right here at the end and just before I get started. Oh, well. So there's a name to an address of where this information is supposed to go. Now, when this gets handled by the routers, and certainly with the analogy of mailing through a post office, they will look at, they being post office, are going to look at this information, this envelope, and try to see how to best route it. For example, if the package is coming from and going to the same zip code, well, it's only going to go to that one post office. It's not going to go outside that, certainly not outside the state, right? But if it needs to go to a different zip code, well, then it's going to get routed to another zip code and then to the city, the state, et cetera. So it gets routed based on that zip code, then out to the street and then to the house number, and then where it's delivered to that address. Now, something to note is that when the package here is delivered to that address, the mail person does not just walk into your house and deliver it to you personally. There's this kind of a barrier where they hand this off, be it a mailbox or whatever. And a router is somewhat like that. You're going to see what I'm talking about when I talk about network address translation. But that package is going to come to a barrier, and then it's going to get routed inside or to the inside of that area. In this analogy, it's going to be inside the house. So when we talk about the routing of data for using IP addresses, we're going to talk about an IP version 4, and we have those 4 octets. Well, those octets are because each of those ranges go from 0 to 255 using binary. And we use that to help understand a lot of that addressing and what differentiates one machine to another. And as we pull apart that IP version 4 address, you see the binary representation, and also with version 4, it's 32 bits. With IP version 6, I believe it is 128. So there's 64 for the network addressing, and then 64 for the host addressing. And I will show you with that right now, because the first thing that we have with IP addressing is what's called a subnet mask. And the subnet mask helps differentiate for the router, what is the network side versus a host side. And that host, you can think of it as each laptop that you have is one host. Every game system you have is a host. Every washing machine that is on the internet is a host, right? And then the ones that are represented as the network are all the ones versus the zeros. So when we see this difference here, we have the network address versus the host address. And one of the things that we look for with that subnet mask is, where does the ones turn to zeros? And you notice that with a 255 subnet mask, the 4th octet is completely representing the host, where if I did a 254, I'm stealing a bit from the 3rd octet, and now my number of host has changed, but my number of host has doubled. My number on the network has decreased. Now, this helps us with what is called the ranges of IP addresses, and the ranges that are being classified. There's actually 5, but class D and E are for extremely specialized uses. The ones that are used in public are going to be the A, B, and C. Now, this will differ in just a moment, just slightly, because we'll talk about CIDR, where it's actually classless interdomain routing, where if you're familiar with your Cisco routers and maybe even a Juniper router, if you deal with anything that is for heavy stuff between either corporate offices or city to city network traffic, things like that. But you have these class ranges where class A is going to be starting from 0, and going out to 127.255, etc. And then B will pick up from the 128 and C picks up from 192. And from there, you can see the number of networks to the number of available addresses. So you can imagine that if you have an IP range, and that is a class A, you can hold a great number of addresses as far as host, but not that many networks. So there are things that are called non-routable addresses in the
Hey,
RFC
Sean,
19.
can I
Yes.
stop you for a second?
Yeah.
Are you okay when people have questions, if they interrupt you?
Oh, yes. I'm sorry. I was supposed to bring up
Okay.
the chat window and I forgot.
Yeah,
But yeah,
we
please do.
didn't, they haven't asked any questions, but we forgot to cover this earlier. So if you do have questions for Sean, you can interrupt him, or if you want, you can throw them in the chat and I will monitor the chat. So you don't have to, Sean.
Yep.
And
Okay.
when questions come up there, I'll bring those up. So if anybody wants anything clarified or anything like that, then please talk to Sean or talk to us in the chat.
Yep. I know a lot of people don't
Starting
like
now.
to come off mute, and sometimes you get the barking dog behind you or whatever. But you're more than welcome to put a question in chat. Yeah, Eric's watching it. I'm watching it. So we want to make sure that your question gets answered. All right. So when we talk about the IP ranges, there are a subset of ranges that have been set aside for private use, meaning that if you have an IP address for your laptop there at the house, chances are it does not have a public address, but it has an internal address. And that's based on one of the ranges here, this defined by the RFC 1918. The reason for that is so that the private communication stays inside that LAN, that inside that router. Is then if you will need to go outside of that, then the router will actually work to that based on the destination address. And there's a little bit more to that. We'll get into that in just a second, but this is where you can see that CIDR notation. If you have a 10/8, it means it's going to start at the 10.000, and it has a full 16.7 million available addresses. Chances are, depending on which router you have, you can change these, of course. You probably are starting with a 192.168 address, in which case there are 65,536 available addresses. So why do we need to know a lot of this stuff about the IP ranges? Well, when we are trying to put together a network, and be it on premises or in the cloud, where I do a lot of my stuff, we need to understand a lot of what do you need to do? How many hosts do you need? And what is that going? What are the purposes for that? And so we get into this thing for network sizing. And the network sizing helps us to understand how many computers are we going to put on there, as far as, and as well as if we're going to use any sort of VPN connections or the inner sizing restrictions on that, etc. So given a first example, if I'm using a /24 CIDR range, so it means there's 256 available hosts, I'm taking up the entire fourth octet. So in this case, I'm going from the 10.0 out to the 10.255 range. However, if I move that just slightly and say, oh, sorry, let me define this out. So there's that 24 with the /24. I'm using up 24 bits on the network side and showing that I have full 256 available addresses on the host side. So if I modify that slightly, instead of being a network of 256, if I change that to something like a /23, well, then I've doubled my size. So now I can go from a 10.0 out to a 10.0.1.255. Now, essentially taking up 2 of the /24 spots. If you do something like virtual networks and you are a VPC in AWS, you have to have at least one subnet. That subnet can take up the entire range of the VNet if you need it to, or you can split that out. All right. And let's see, yeah, you can you can break those apart depending on how you need to. For example, if I went back to a /24 on the VNet, I could just use up 128 addresses. The point here that I'm making is that they don't always end, or they don't always start with 0, and they don't always end with 255, depending on the size of that network. And you'll see where that makes a much bigger deal when we get into the cloud here in just a second. So you can also break them up. You notice that they are broken up on the binary boundary, meaning that they're in twos. So with a /23, I've got the 512 addresses available, but I can take up 128 here, another 128, take the rest up in 64s. I can break this even further down to maybe the bottom one. I can break up into two 32-bit ones instead, 32 addresses, sorry. So there's several different options when you come up with a network sizing. And again, you want to understand where you begin and where you end. So this comes back to, why would we want to have multiple subnets, and how would I understand the size that I need? When I say size, the number of hosts that I need. So one of the things that we'll do is segment them. For example, I may have a subnet that is entirely set for the DMZ, where I've got public-facing resources, something like an Azure load balancer with a public IP address, or maybe it's a virtual machine with a public IP address, something like that, that is public-facing. Well, I can have other resources using up different subnets, and they don't have any kind of public access, and they can only be reached by internal resources. But I may also segment them by different purposes, for like web resources. Maybe I got some app servers and maybe database servers, etc. When I use segmenting by these subnets, it allows me the opportunity to provide extra security and rules, maybe even firewall rules, to help protect those different resources. So let's dive in just a little bit more on that CIDR that I've been talking about. And, I was using /24 to represent those, 24 bits are taking up with the host. I'm sorry, with the network size, which gives us 256. Now, obviously, this is a small table. You can go all the way to /0. But you can see how everything's divided by 2, divided by 2. So if I do a /29, I get 8 available addresses. And if you're familiar with VLANs at all, you'll know that the first address and the last address is always reserved for the gateway and then the broadcast address. When you get into the cloud, they take 5 addresses. So what I'm noting here is that the /29 is technically the smallest that you can have when you are defining a network or a subnet, because 5 of those addresses are going to be reserved. You do anything smaller, there's not enough to supply the required ones. Now, I mentioned /32 is the most specific, and what you'll see is if I want to add like my own IP address into a firewall rule, sometimes you'll see /32, meaning it's this one IP address, it's not a range. So all bits are set to 1, and this is the most specific way of declaring that address. Okay, so let's get into network address translation. And we were talking about how on on your laptop, you're going to someplace like google.com, or better yet, go to improving.com. How's that? And you're going across your router and going to the internet, and you're going to hit a website server. And you may have your laptop, it will have an internal non-routable address. Well, if it's not routable, how does it get to the internet? Well, this is where that LAN side to WAN comes in, and that what that router is there for. But that router is going to have a public IP address. So public facing, probably from your internet provider. And so now And by the way, you can do this wherever you are. You can get to a website called whatismyipaddress.com, and it will tell you what your public address is on the outside of that router there at your house. So if I'm going to go hit a website, how does that traffic go from the inside to the outside? And that is what's called the network address translation. So the router is using basically a lookup table, and it's kind of adding an entry. It says, well, there's an outbound request going out to the internet. So it's going to record that IP address. And then when the reply comes in from that website, it's going to come back to that public side, and the router will take that data, those packets, and then we'll route them back to that private IP address on the inside. So that's what's called network address translation. Now, if you have a second device, as we all do, then it's going to have its own internal IP address, but it shares the same outside address. So that's where that table is used for being able to route that traffic coming back, except for that's only the IP address. How does the reply know as it's coming back to that router on that 40 address? How does it know which of the source laptops did that request come from? So what we have in addition to that is what's called port address translation. Now, this is in addition to that network address translation. So what we have instead is that the laptop, say that 0.5 laptop is making a request out, it has a port that it's using. It will open that port. You can think of it similar to a WebSocket. And so it's open that port for that conversation. The router is going to use its public-facing IP address, and it picks a random port number and very high number. You notice that the ports go from 0 through 65,535, but the first 1024 are reserved. So it's going to pick a high port number, and it uses that for that traffic going out. When the reply comes back in, it knows to come back to that address as well as that port number. And then that's what the router is using to get it back to the original source for that request, and it doesn't go to the wrong device. So when another device is using that same thing, even if it's going to the same website, if you're both laptops are going to google.com, it doesn't matter. They're going to have separate ports on the router for that. But it gets worse, because that's per device in this analogy. But as we all do, all of us are going to have more than one tab open and probably more than one browser. For each tab that's open, the reply has to come back to the correct tab as well. So it's not just about going to the right port, but tab. So what we have is, for each tab, you have another port that is open for handling those requests. So you can get, and it's rare as far as our laptops, but you can get this certainly with traffic, production traffic on the cloud, for example, thing called port exhaustion. When a port is used and it's still working, it still has data going through it, it's going to remain open. After a port is no longer being used and there's no more traffic, it will sit idle for a certain amount of time. And then finally, the router will close that port and make it available for another conversation going out. So you may be familiar with
that.
I'm sorry,
if you don't mind. Yeah, question about that. So how does that conversation between the NAT router and the computer happen? Does the computer request and say, hey, I need to open up a separate one because it knows that it's running a browser with multiple tabs? Or is it the browser communicating something? Because the NAT router is not going to know.
The router is not going to know anything about the tabs. So your computer, the OS, is going to know that it needs to create another essentially another socket out there. I'm going to say that kind of loosely. It's not always a web socket per se. but essentially a socket. And for each of those tabs, and you start working with a network conversation that's certainly new, it's going to grab another port. Now that's going to be from the laptop. So for each request to the router is another port. And I should have added that on here. And in fact, I'll do that after this talk, as I'm going to modify this, because that's a good point. For every tab that you have open, you're going to have a port, and those ports are on the laptop itself going to the router. So the router is keeping essentially a list of active communication. And so it's going to have the source address and port to the destination address and port, as well as it knows its own IP address. So it knows the open ports going out on the public side, so that when there is return traffic, it knows how to route that from the port back to the originator of that request. If it is not originated inside the net, inside the LAN side, but instead maybe I've got a web server and I'm hosting it, and you can tell your router to open up port 80 or 443, for example, and then or even like 22, port 22, and I'll explain that in just a second. If you tell your router to open that port as a listener, but also when that happens, you're going to route traffic that comes in on that port. Let's just say it's port 22, and you get routed to one specific device. And that is also called port address translation. So it's not just the network side of the address translation, but also the port. So you can host a web server on the inside of a router, but you have to tell the router to open that port for listening, but also where to redirect that request coming in inbound to. Generally, like when we talk about cloud-based stuff, we're going to go to a load balancer. The quickest way, if you're not doing cloud, you may go to maybe a device that is a virtual an appliance that's sitting on the rack that is acting as a load balancer. Or if you want to do what's called layer 7, which I'll get into in just a moment, Nginx has a load balancer, in which case it's going to end up on a server, the requests come in onto the server, and then get load balanced across different sites being hosted. So did that help answer the question?
Yes, it did. Thank you.
Okay, good.
So
All right.
one more
Yes.
question. So these ports that it's opening up on the outbound, is that what you're like, if you run netstat, is that what you're seeing under the local
Yes.
address is the outbound port, and then the foreign address is basically what you're connecting, like the HTTPS port?
But basically what you see is the netstat's going to show you ports that are, first of all, to the device. So
Mhm.
you can run netstat on your laptop. It's going to show you all the ports that are in different states, and so you can use different switches to show all those that are listening, for example. They're not necessarily the outbound ports per se. A port is just a port, but how it's used is what makes the difference. If I see port 22 is listening, then I'm listening for what is predetermined as SSH traffic, that secure shell traffic. If I have port 53 open and listening, then I'm listening to DNS traffic, hence my chart that I'm showing here. And for example, if I'm hosting a MySQL server, and I want, or even through replica and stuff, and I want to open up ports so that I can receive incoming traffic, then I'm going to open up 3306, and netstat will show that as 3306 listening. You can also, depending on the switches that you use with the netstat command, see those other ports, and they're going to be like really high numbers, really to stay out of the ranges of what's commonly used for inbound. And so if you see something, I don't know, maybe 10,000 and above or 20,000 above, generally those are going to be for a conversation handling going outbound. But yes, netstat, you will be able to see them. Did that help answer that question?
Yeah, perfect. Thank you.
Okay, awesome. So yeah, we have these predefined ports. I say predefined versus common. Um, Years and years ago, I was doing a lot with FTP. So 20 and 21 for the command and versus the data. So you're using 2 ports for that. 22 is commonly known for SSH, 25 for small mail transport protocol or simple mail transport protocol. DNS for 53. And then 80 and 443 is what were more commonly used for HTTP and HTTPS traffic. And then if you're familiar with 1443 and 3306 for the SQL Server and MySQL Server, respectively. And a quick note, I've always known that DNS uses UDP for its conversation. And I did not know this until just recently, but DNS will also use TCP if the reply is not working on the UDP. So if you are setting up in kind of firewall rules, you definitely want to use or open it up to UDP and TCP so that DNS can use TCP as a failover talking protocol. So when I'm talking about these talking protocols, what exactly do I mean? There is a thing called an Open Systems Interconnect model, the OSI model, that many people may have heard of, and generally it is a general representation of conversations that happen at various layers or levels. And essentially, layer 1 deals with the physical. And that's when we're going to talk about, you know, what kind of fiber are we using? Are we talking about copper? Is it Cat 5, Cat 6, 7, etc. And then as data is received on that physical medium, and then it goes through 2, then 3. Network layer is for your IP addresses. Layer 4 is where you have the TCP and UDP. Think of that as similar to when I was given this analogy of a passenger train car, where the train itself is going to go back to from one station to another, but it's going back and forth checking, you know, did you get the people there okay? How many people were there? I'm going to try to load this many people over there. Did you get them all, etc. It's very chatty versus UDP, which is user datagram protocol, is not chatty at all. Instead, it's almost like a fire and forget. It's you can think of it as I've got a message, here it is, hope you got it. And the protocol itself is not worrying about the reception of the message. Then we can go up through, I say 6 is used for, you can use SSL, or SSL is dealt with on layer 6. Depends on the model itself. Generally, this is 6. Sometimes somebody may express this as being done on 5 and 6. It doesn't matter. You can kind of see what it's there, so that the there you go. I like that. TCP is more like American Airlines, and UDP is more like Spirit Airlines. That's funny. So SSL secure socket layer is now been kind of evolved into TLS, transport layer security, and that is still, you know, like an evolution of the encryption of the data, encryption of that payload, and that is done at layer 6 generally. Layer 7 is for our applications. Once now everything, that package has been, that payload has been decrypted, and now our applications can make use of that. I mention 4 and 7 specifically because if you're using something like an Azure load balancer or an AWS network load balancer, those operate on layer 4. They help care about the IP address as well as those protocols used for the packet handling, TCP versus UDP. So they're done as a layer, known as a layer 4 device. But a layer 7 is an application. So things like an Azure App Gateway, AWS application load balancer, or even like an Nginx load balancer uses layer 7. Another quick analogy on this is if you're familiar with MVC programming at all, if you have like for example, ASP.NET MVC, the one letter they leave off is routing. So as that request comes in, it gets routed to a controller. And that routing to a controller is done at layer 7. And then as that controller will handle the logic from there, have its views created, and then the reply is set up and then sent back out. And then it's going to go back down this list here. So it goes across maybe a physical medium, maybe fiber out of that server, and then also across routers to other routers, hop, and then back over to the laptop that made the request, for example. Okay. There is another, I say kind of paradigm. This is considered, it's a security paradigm, if you will, a security model. It's called north, south, east, west. And if we're hosting many different services, we're going to have items in our DMZ that are public facing. Then we'll have stuff maybe in the app server layer, hosting many different applications, and then multiple databases in the database layer. Now, what we don't want is traffic from the internet going directly to the database. That's just wrong. That's not very secure at all. So we put things in front of that to help protect data integrity, such as our applications, etc. So the north-south is the internet coming through the DMZ over to our app services and then to our database, etc. Sometimes we want to protect how that traffic is going and who can get across there, what ports are they using, what conversation are they having. You'll see firewalls in use for this. It is possible to do a secure shell, that SSH, over a port that is not 22, and doing so may trigger a firewall that's doing packet inspection. And then you got things like IDS, which is intrusion detection, which is going to simply flag it and let you know about it, versus intrusion protection or prevention, in which it's going to stop that traffic and not allow that to flow through if it says, this does not belong. And of course, you can add in many other different type of rules based on what you need there. The east-west is representing the conversations between servers on these their different and respective layers. It may be where you have public facing servers that are there to receive traffic, to receive those requests inbound, but have absolutely no business talking to each other, in which case you can use something like a firewall to help prevent that traffic. Coming down to like an app service layer, another east-west layer here, is you may have app servers that, again, have no business talking to each other. And if they try to, then you probably have some rogue code that got on there, and it may actually be trying to sniff the network so that it can gather some data and send that out. That does happen. So your best bet is to, you find those services and go, they have no business talking to each other, add them to a firewall and get that blocked. And sometimes there are the cases where they do need to talk to each other, in which case you do allow that right there. So just making sure you're aware of that capability and that security model. So now we're going to get into kind of a cloud networking in the Azure, for example. And this it's the same concept with AWS. You have a virtual network, and I'll describe AWS in just a moment, but you can have a virtual network. And here I'm saying I've got a VNet the size of a /23, so I've got 512 addresses. I'm going to split that up between two different subnets, and I've got a 10.0/24, then a 10.01.0/24. But I also have another VNet, and it happens to be on the same VNet size and the same subnet size. And I want to peer them together, maybe because we've got servers running on both VNets, and I would need them to talk to each other. The problem is, and this is where VNet sizing comes in, if you size something too large, you're more likely to hurt yourself. If you do it too small, then you have to do some leapfrogging by creating yet another subnet that's larger, etc. And so you definitely want to spend some time understanding your needs and give yourself room for growth on each of those subnets. So with a virtual network, if I needed to peer to another one, the addresses cannot overlap. Here, for the sake of a simple example, I'm just saying that they're identical. But if they overlap at all, that size overlaps at all, you cannot do a network peer. Then the only way to do that is by VPN, and then it gets trickier than that because then you got other translations going on. However, if this other VNet happens to be on a different network address entirely, here I'm saying a 10.1, 0023, then that can be peered, and then the servers or VMs or maybe I've got a SQL server, an Azure server, I'm sorry, Azure SQL setup or something like that, or even a storage account using private endpoints. Now I can allow them to talk to each other. I can use route tables to help force traffic to different areas. And this is definitely, I mentioned the use of a firewall, but if I want to force traffic to that firewall, then I can set up a route table, apply it or associate it to a subnet, and then say, well, if you are traffic bound for the internet, which is that quad 0/0, which is essentially everything else, then I'm going to forward that traffic to a firewall, and maybe I'm using what's called an NVA, network virtual appliance. And then in which case I give it the IP address of where that is as the next hop. And then you can have different route tables, and you can associate a subnet to the same route table or different route tables. In AWS, there's a thing called a virtual private cloud. Acts very similar to Azure. They've got VNets. You cannot overlap, certainly if you want to peer. And subnet sizing is done the same way. Now, one difference is when you create your AWS account, you do get a default VPC, where in Azure, when you create your account, you don't have a virtual network at all. However, if you want to create a virtual machine, you have to have a VNet first. Every virtual machine is required to have a virtual network first. Here, I'm saying that you can also use route tables in AWS, same thing, but they also have a concept of public and private subnets. And here, the only difference is that the subnet 1 in the route table has what's called an IGW, an internet gateway. And the fact that there is an internet gateway and that it's allowed for traffic to go out says that it's a public subnet. Whereas the second subnet is tied to the route table B that does not have an IGW, therefore it's considered private. So if you get into some of the AWS literature like I have and trying to understand public and private, and it took a while for me to understand where that was defined at. I kept looking for a switch so that I can just flip a switch and make it public or private. Never was a thing. Finally understood it was the existence of the IGW. So if it's there, it's considered a public. And it's only because it's allowed, traffic is allowed to get out to the public, to the internet, and basically outside of the virtual network itself. Okay, load balancers. When we look at our services that we are providing, our applications, we're hopefully not just have one and hope it's 24/7, but instead we have multiples. Well, when we have multiple services instances or VMs or whatever we have, we need to share that load and prepare ourselves for anytime we need to pull a service away for a code update, or if we're doing VMs, maybe we're doing patching, things like that. Hopefully you're not doing that, and it can go with service options. But you still need to share that request load coming in. So we have load balancers for that. But there are different types of load balancers. I mentioned those earlier. So with a layer 4, and this is dealing with TCP and UDP, so IP addresses as well as the kind of the talking protocol. If we use a layer 4, then we're going to use an Azure load balancer or an AWS network load balancer. Whereas if we have layer 7, we'll use Azure App Gateway or an AWS app load balancer, application load balancer. And it is possible, because I've done this, you can have a network load balancer that forwards traffic to an application load balancer that goes to the AWS API gateway. So now you've got one device that is for if you want to do a service endpoint, and it's private facing, but it only operates on layer 4, you can have that still routed to an application gateway. The API gateway, an AWS, which only operates on layer 7. So it is possible to connect those from network over to the application load balancer. All right, in Azure, we also have a thing called a network security group. And AWS has something very similar to that as well. They're what I would call a lightweight firewall. They're based on rules, but they do not do packet inspection, meaning that if there's a hacking attempt across a port, if you're going to do like SSH across port 53, and I'm just giving a wild example, it's not going to necessarily try to determine if that's a good traffic or not. For that case, you do want to use a firewall that does have that packet inspection capability. But with these network security groups, you can set up rules that apply for traffic either inside, or I'm sorry, for inbound or outbound of the subnets and or the NICs that they are associated with, those network interface cards that they're associated with a VM level. And they are what's called stateful, meaning that if I have a virtual machine and I'm just there maybe as a jump station, a jump box, and I'm there and I want to make a request out from that VM, and I want to go out to maybe another, maybe I just want to approve some outbound request, and maybe I want to go over to like Weather Underground for an API call type thing. The request will go outside of that VNet and go out to the public, and the request needs to be able to find its way back in. And this is that stateful nature, much like I mentioned with a router that keeps track of outgoing requests, so it knows how to route those the replies coming back in to the originator of that request. That is a network security group does those as well. AWS has what's called a network access control list, which is stateless, in which case one rule does not mean that you can, that it applies in both directions. You're more often going to use a security group, but it is still a product that they have available. So, okay. I am done with this piece of it. Are there any questions that I can help with before we finish up?
Anybody, feel free to unmute yourself if you have a question. Even if you think it's a basic question.
Oh, yeah.
Oh, good.
So if you have a router at home that offers something like device isolation, like what's actually happening with that? And
Device isolation.
yeah.
If I am understanding that correctly, that is when you have your device can get out to the internet, but it cannot be seen by other devices on the same network. And you'll also see that when you connect to like a Wi-Fi connection with Windows, and it says, would you like other computers to be able to see you? You want to share your information out there on the network, you can say no. And then if somebody's sniffing the network, they're not going to immediately and quickly be able to see information about your computer, even though if you're on the same network, it'll block that.
Cool. Thanks.
Okay.
Yeah, if you've got a few virtual machines running on one physical device, I think each one of those virtual machines has its own IP address kind of ish thing.
In Azure, so in Azure, every virtual machine has at least one NIC, the network interface card associated with it, meaning that they have at least one private address. A NIC can have more than one, depends on the size of the VM that you get. And if you do like a B series or an A series or a B series, you're not going to have this. You'll just be stuck with the one IP address. But there are other sizes like in the D, E, and F range, at the very least, that you can have you can have more than one network interface card to the VM. And you can have what's called a NIC can have what's called an IP configuration. And that IP configuration is what holds the private IP address and a public IP address if you want it to. If you want to do more than one something I've done is I used one VM that had 4 NICs, and each of the NICs had a private IP address, and I was using it, and each of those NICs were associated to different subnets on the same virtual network. That way, I had one channel between its clone. I had one channel so that you could do health checks, and I was able to do the public facing traffic. So I had a public Azure load balancer, and then another one for the internal traffic that it was protecting. So I was using that as a firewall, and I had a custom installed firewall of Fortinet installed, but you can also use that with Palo Alto's firewall as well. And that, in a sense, when I'm using a custom firewall installed on a VM, that's also what's called a virtual appliance. And I can treat it as a virtual appliance. And then I had my route table associated to different subnets. And I said, if you have traffic originating from this subnet and you are going to this address, you are routed and forced to go to that firewall first. And that way, every bit of traffic was scrutinized. Yeah. So it depends on the VM as to what capabilities you have, but you can do that. And with the private IP address, you can choose if it's a dynamic or static, which is interesting because the operating system on the VM, for example, Windows, when we like to, Windows has the idea of a static or a static IP address or dynamic. Windows will always think it's dynamic. And you can screw yourself up by trying to go make it static and make it something else, and then you just have no access to your computer. And you got to kill it and rebuild it. But a NIC can have a static IP address, and all that is telling is that the IP address came from the subnet by DHCP, the dynamic host control protocol. And all that does, the subnet says, well, I'm going to declare this as a reserved IP address for this NIC. And that's all a static is. What other questions? I like these. Get me to scratch some neurons. And there's a lot more in depth that we could do as far as, how does DNS work? I have never tackled bind, but bind is very similar to DNS for that, certainly for that purpose, but it's mainly on Linux that you'll see that. DNS has the root plus the domain plus something else I completely forget, but there's definitely degrees of how a DNS actually works when it, you had, for example, you've got a computer, it says, I don't know the answer to that. I don't know where usergroup.tv is. And it knows how to go to the .com, which is a root server. And it says, well, I don't have that one specifically, but I know you can go to the domain server. The domain server is located at this address. And then it goes to that address and says, hey, I'm looking for usergroup.tv. And then, okay, good. Well, I've got this one here. And then it goes to the either like this is where I'm forgetting it off the top of my head. And then it goes to it ends up in a server that says, yes, I know exactly what you're talking about. Here's the IP address. So then it comes back to your computer, and then finally that request gets routed to an IP address because the name has finally been resolved to an address. All right, what else?
Back on the slide where you had different classes of addresses, do you have examples of like what would use those different classes?
Oh, like the class A, B, and C.
Yeah.
Where did I have that? Right there. Okay. Generally, if you had like what's called a SOHO, small home, no, was it small office, home office type router? Generally, you would see that as maybe you have a network that, you know, on the inside of that router, and you're going to use a class C for that. And so this is more where you have something like it's on premises, or if you get into VLANs, things like that. A VLAN and let's cover this right quick. A VLAN is not a VNet in the cloud, and a VLAN is closer associated to a subnet in the cloud, but they still operate very differently. A VLAN, I believe, is more of a layer 2 or 3 versus a subnet. So generally, you will see the class ranges here if you are dealing with, for example, if you're working at a corporate office and you've got several different departments, and let's say there's 50 different departments and you're going to use multiple routers for that, you might end up in a class B for handling that, so that you can divvy up those different departments into ranges of IP addresses of what they're available to have. The other thing too is this is public and private shown here. So you will see IP addresses that are in the class A. So like my home address is provided by Cox Communication here out of Tulsa, and that I can tell by the first octet it's in the class A range. So but that's just more because they've got a block of IP addresses, and then they start doling those out to their subscribers. Does that help answer that question?
Yeah. So like ISPs and stuff are generally the ones that are going to be having class A's.
Yes, they don't have to. Sometimes there'll be a class B that they're given. There really is an ultimate control of the IP addresses, because essentially we have already ran out. And that's when, and I briefly mentioned this, where IPv6 is now here to kind of help solve a lot of those problems where we have outgrown. And so an ISP, say some mom and pop ISP provider out of a small town, they're still getting a block of IP addresses from another provider above them. And that could be MCI, that might be AT&T, things like that, where they're a block owner at a high level.
Oh, okay, cool. Thanks.
Yep. Mm-hmm.
Yeah, so I just did an NS lookup on google.com, and I found some of the answers that came back were IPv6 addresses, and I think only one came back IPv4. Why is it at this point that we don't have to see IPv6 all over the place? Why is IPv4 still around if we've run out of addresses?
Why is AS400 systems still about? Why are COBOL and RPG still used? A lot of it is because of slow adoption, and there's not enough people being forced to do that. I say that, but not meaning to sound like a judgment call. There's just not enough adoption and people being forced to go that direction. Also, IPv4 is extremely easy to read, certainly as you understand how to break it apart, and certainly a lot easier to say with an address, whereas IPv6 is now represented with hexadecimal letters, and it's almost as getting as difficult as trying to read off a barcode, something like that, thin, thick, space, thin, thick, that kind of thing. So it's just hurting some of the adoption. What else? Awesome. Well, thank you guys for having me. I appreciate it.
Thank you, Sean. Really appreciate you coming out. Anybody else have any last questions, comments, anything anybody wants to discuss related to this?
I just love the UDP analogy when you're talking about people in a car. It's like, okay, TCP, you got an engine, you've got a bunch of cars, you got a caboose. It's like, okay, we're going to make sure they're there. UDP, get on the car. I'm just going to kick it down the track. Good luck.
Yeah. When I've done this talk in person, I will, and I've done this at Kansas City Developer Conference and other places, and I'll just randomly get a volunteer in the audience and say, okay, I want you to help me out. They have no clue what I'm about to do. And I go, we're going to talk TCP. And I'll talk to someone. Okay, what's your name? Diane. Diane. Okay, great, Diane. Hey, Diane, I'm going to send you a message. Are you available? Oh, you are. Okay, great. Diane, I want to send you just a small payload. It's just a hello world. Okay, okay, you got it? Okay, good, good. I want to send you a larger message. Can I send you a larger message? Good. Okay, good. Here's the larger message. Okay. And I just go with this dialogue back and forth. And okay, Diane, I'm going to send you a message. Oh, you didn't get it? Oh, okay, let me resend that. Okay, here's the message. Did you get it? Okay, you got it. Good. Okay, that's awesome. All right, now. Okay, UDP. Hey, Diane, your car's headlights are still on. Hope you got it. That's it. I mean, so there's a nice little quick dialogue of a difference between TCP is extremely chatty, and we still use it a lot. And it's still very dependable in a sense, but UDP is there for those quick shot type messages, and it itself does not care about the reception of the payload.
Mm-hmm. Yeah, when I was first learning about TCP, I kind of locked on to what somebody said at some point, that it is guaranteed delivery. And it was a very painful lesson for me to learn that that's actually not true. So what guarantees do you get with TCP?
It is a good, well, certainly out of a limited number of protocols like that, it's the best one that does the best attempt of a guaranteed delivery. But in itself, if it's just broken up and it just doesn't work, then you're going to just see other application issues, in which case then you get into what Michael and I have talked about quite a bit on, is the CAP theorem, right? So then you get in what's called that network partitioning between the originator of the request and maybe a destination, and which now, if the TCP is breaking apart, then the error itself, that condition, is going to basically bubble up to the application, and maybe it's Zoom as that application, and it's having trouble sending video or sound, and now you're going to notice that maybe there's pixelation or dropped audio, maybe it's dropped audio quality and things like that. The sampling rate changes. It's up to us as developers to also be able to handle those conditions. So now we're putting in things like retry logic that says, okay, we've noticed this condition. Let's maybe we need to back off, wait, say 20 milliseconds and try it again. So you hope for things like that, hopefully it's a transient issue and that network partition comes back. And then which case is, well, 20 milliseconds, that is a long time. So was there any data that needs to be synced between the target and the source and the destination? And because sometimes what's talking is actually maybe storage accounts, because I can have a storage account that is in one Azure region, another storage account in another, one of the paired regions, and I told it to sync up. I'm going to do some geo replication, but there's a network partitioning in the middle. Well, now that it's come back, even 20 milliseconds later, now it's got to resync and it has to that much more transmission to go across and to see if it can catch up to any kind of data replication that needs to do. What else?
All right, I guess there is nobody else. If that's not true, you can go ahead and speak up. Thanks, Sean, for coming and chatting with us. There's information there about Sean. You can go check out his Twitch, his Twitter, and all those things.
Yeah.
And of course, if you're in Tulsa, you can go to his user group. Thank you, Sean. We really appreciate it. And
Thanks for having me.
everybody, yeah, glad you're here. And we hope next time to have you live in person. And we'll be talking about that later. Thanks everybody else for coming and joining us tonight. We'll hopefully see y'all next month in our next meeting. If anybody wants to stick around and talk for a sec, well, some of us will stick around, but thanks everyone for coming, and we'll officially draw our meeting to a close.